Welcome to the Crypto Kid channel. Today I'm going to talk about the principles of blockchain interconnectivity. So let's get started. Every day, we visit websites and interact with different content from dozens of servers, networks, from different geographical locations. Each web page includes links to other websites from different sides of the globe. What makes these interactions possible? The answer lies in the protocols and networks that have been created throughout decades. And APIs that sit on top of this infrastructure allow developers to send content across the globe. Protocols such as TCP, IP, BGP, and HTTP define communication standards. Internet service providers run the underlying networks. And interconnectivity networks by companies like Akamai or Cloudflare deliver packets efficiently from one network to another. APIs such as those powered by Twilio make it easy to build on top of the stack. Why can't a blockchain space offer the same user experience? Now we are still in the early age of blockchain history. More and more chains are being created. But the ecosystem is really fragmented. Interoperability protocols and APIs are missing. This prevents us from mass adoption since we cannot leverage the ecosystem to the fullest. So what are the key properties that interoperability must possess in order to achieve global adoption? Back in the day, Dr. Venton G. Cerf and Dr. Robert E. Kahn laid out some of the foundations of the Internet protocols and developed the basic interconnectivity principles across networks. So let's take a look at Cerf and Kahn's principles of interconnectivity. Core principles that any interoperability system must satisfy are as follows. First, no changes are required to integrate. Each distinct network needs to stand on its own, and no internal changes need to be required to any such network to connect it to the Internet. Second, best effort intermediate communication. Communication is done on a best effort basis. If a packet does not reach the final destination, it will be retransmitted shortly from the source. Third, gateway-based connectivity. Individual networks should connect to other networks via black boxes, gateways and routers. These black boxes retain no information about the individual packet flows passing through them, thereby keeping them simple, and avoiding complicated adaptation and recovery from various failure modes. Fourth, decentralized control. There should be no global control at the operations level. These principles can be applied to blockchain. So let's apply them to the blockchain space. First, no changes are required to integrate. Bridges like Solana Wormhole or Rainbow Bridge still require heavy engineering. Imagine there is a bridge between chain A and B. If blockchain B wants to upgrade, then its developers need to coordinate with blockchain A, developers on such upgrades, and then upgrade the transition logic accordingly. And this problem scales if blockchain B maintains many connections to different networks. Instead, the integration connector should be as light as possible, and work as a plug-and-play model. Second, best effort intermediate communication. For blockchain systems, the source is often a user or an application smart contract, and a destination might include a destination chain and a contract address that the user wants to invoke. So if a cross-chain packet is dropped, no user should lose their funds, and they should be able to resend from their origins. Third, gateway-based connectivity. For blockchains, this means that each chain needs to host gateway accounts, smart contracts. All information from applications on one chain should be routed to these accounts. These gateways should be easy to instantiate, and they should not depend on the state of end networks. How about we set up the centralized system? Put a central database between a few networks and an API that users can query. This solution does not work, because this means that one entity eventually be able to censor and control who can use the systems. So here comes the fourth property, decentralized control. There should be no global control at the operations level. The entity in the middle should be decentralized. The network needs to include as many validators as possible for maximum security. There need to be both economic and utility incentives to participate in the protocol. The community and node operators must govern the protocol. Malicious behavior needs to be identifiable and addressed at the protocol level. So are there any entities that satisfy these properties? Axelar is one of the blockchain-agnostic protocol that tries to address interoperability issues. It has the property of plug-and-play. Different blockchains don't need to speak the same language. The cross-chain protocol should be able to plug in any existing or new blockchain frictionlessly. Apart from that, it also supports upgradability. If one of the blockchain ecosystems changes, it should not affect the interoperability of other blockchains. Axelar provides uniform language for applications. Application developers should be able to use them for communications without rewriting their software stacks. Axelar uses large sets of validators with delegated proof-of-stake model to create a secured and decentralized network. It also has a strong slashing rule to prevent validators from cheating the system. And it also has robust fallback mechanisms. In summary, Axelar contains all 4 properties that interoperability protocol should satisfy. Axelar is still in the early stage and there is still a lot of work. For example, plugging in every new blockchain to the protocol, maintaining the security and liveness of the system. However, if different blockchains can connect smoothly, the benefits of the right architecture are tremendous and it will make mass adoption possible. That's the end of the video. Thank you so much for watching.